Hello, my name is Hugo, and I will present our paper Fully Dynamic Electrical Flows, Maxflow in m to the 1.497 time. This is a joint work with Yang Liu from Stanford and Richard Peng from University of Waterloo and Georgia Tech. In an undirected graph G with edge capacities, the Maxflow problem asks whether we can route some fixed amount of flow between two vertices. The flow on each edge should not exceed the edge's capacity, and because the graph is undirected, the flow can go in either direction on one edge, but not both. In every vertex other than S and T, the amount of incoming flow should be equal to the amount of outgoing flow. By some classical reductions, the general max flow is equivalent to the decision version where we have a single source, single sink on an undirected graph. And this max flow problem is well studied in the past decades and has numerous applications in scheduling, image processing, network science, and so on. This slide shows the previous combinatorial algorithms on the Maxflow problem, starting from Ford and FOCS. So in 1998, Goldberg-Rao had a breakthrough result, and they gave the first combinatorial Maxflow algorithm that runs in about m to the 1.5 time on general graph. In 2008, Ditch and Spielman showed that one can use the Laplacian system solver to implement steps of an interior point method and achieved an algorithm that matched the runtime by Goldberg-Rao. The interior point method is a method for solving linear programs, and the Laplacian solver can be viewed as a tool to solve electrical flows. After their result, there are a lot of algorithms that follow their numerical way to solve the Maxflow. For example, in a recent work by Brent, Lee, Nanokai, Peng, Thornrock, Sitford, Song, and Wang, it is built upon the dynamic process view of flow augmentation. So the interior point methods can be viewed as updating the flows using a sequence of square root of m slowly changing linear systems. So they maintain the solution of the linear systems by data structures, achieving O m plus n to the 1.5 runtime, which is nearly linear on dense graphs. And in this talk, I will briefly introduce our new randomized algorithm that solves the Maxflow problem in nearly m to the 1.497 time. And when the graph is sparse and has polynomially bounded capacities, this is the first algorithm faster than the m to the 1.5 algorithm by Goldberg-Rao. Our approach uses data structures to speed up IPM as well. We consider data structure problems that arise from applying the variation of IPM of the matrix 16 paper. The linear systems in our algorithm correspond to a sequence of electrical flows as well. So after the submission of this work, the bound is improved and generalized to 1.483 for minimum cost max flow in general graph, and nearly linear for planar minimum cost max flow problem. And our paper works only for Maxflow without cost. So the first part of this talk will be on the interior point method, and this is the reduction from Maxflow to dynamic electrical flow. Then the main part is the data structures we use to maintain the high energy edges in dynamic electrical flows that occurs in the IPM. We first introduced the variant of the interior point method we used from Matrix paper in 2016. We maintain flow F, which is initially empty. At each step, we augment F by sending a small fraction of the demand from S to T. So let alpha be the amount of flow that is already sent. The current flow F should satisfy the flow conservation property, which means that for any vortex other than S and T, the total incoming flow should be equal to the total outgoing flow. And for S, F should send alpha units of flow out. For T, F should send alpha units of flow in. And to ensure the capacity constraints, we define a penalty function. So here F is the flow vector and U is the capacity vector. Fe for some edge E is positive if the flow goes in one direction and negative if it goes in the other direction. Thus, Fe must be no less than negative UE and no more than positive UE. So we put log barriers for both such that the penalty function approaches infinity when F of E approaches either its upper bound or its lower bound. So we maintain a flow F that satisfies the conservation property and that incurs minimal penalty, while slowly increasing alpha to the required amount of flow. And in each step of this process, our goal is to send more units of flow from S to T, while keeping the optimality of F. So if we ignore higher order terms, we can see that the augmenting flow should be approximately the electrical flow from S to T, where each edge's resistance depends on its capacity and the flow on it. Thus, by the interval point method, we can reduce the Maxflow problem to solving a sequence of changing electric flow problems. For electrical flow, we will use this combinatorial interpretation of it. It is equivalent to the physical definition. The electrical flow is the expected trajectory of a random walk from S to T with consolations, where the probability of choosing an edge is proportional to its conductance. And by a random walk from S to T, we mean that the random walk starts at S and ends once it hits T. So by this interpretation, the electrical flow on edge E is the expected number of times the random walk uses this edge E in one direction minus the expected number of times it uses E in the other direction. And the potential phi V is proportional to the probability that the random walk from S to T widths V before it ends. So we will not use the definition by Laplacian matrix. And this is the pseudocode of the IPM we use. So we let mu indicate the amount of flow to be routed, and we wrote 1 over square root of m fraction of the remaining demand in each step. So there are about square root of m steps, and the resistances of each step are defined as in the code. It depends on the flow and capacity on the edges, and we calculate an electrical flow with respect to these resistances. And then the current flow is augmented by a small amount, delta mu, according to that electrical flow G. So note that the electrical flow is just an approximation of the true step on the central path. So we still need this recenter step that bring the flow back to central path. And here let's skip the details. So in general, electrical flow is non-zero on every edge. So it takes O of m time to perform a step. And the total time of this framework is about m to the 1.5. Our key optimization over that is lazy updating. Intuitively, when the resistance on some edge changes slowly, we do not need to update them at every step. So approximations to those edges are enough to make progress on the central path. So we can update them together when the changes accumulate. And when the resistance on some edge changes fast, we will make use of a data structure to find these edges and update them at every step. This corresponds to finding edges with high energies in an electrical flow whose resistances are dynamic. And the following is a short version of how the trade-off on runtime works. We have two kinds of edge updates. We use data structures to track the large updates in every step, and the small updates are updated in batch. So we first count the number of large updates in each step. This corresponds to the number of edges with large fraction of the total energy in the electrical flow. So if we track the edges with at least epsilon squared fraction of the total energy, then there are epsilon negative 2 such edges per step. So since the total number of steps is square root of m, we have square root m epsilon negative 2 large updates in total. We use a data structure which is called Locator for locating high energy edges. And our data structure is influenced by the dynamic approximate effective resistance data structure of a previous paper by some of us. The locator initialized in m polybeta inverse polyepsilon inverse time. Their beta is a parameter less than 1. And each single edge update costs m beta time. And the locator expires after updating at most m beta edges. Then we will need to reinitialize it. And locating one high energy edge takes also O of m beta time. So here if we set beta to be epsilon cubed, then the total time spent for large updates is square root of m times epsilon negative 2 times O of m beta, which is equal to O of m to the 1.5 times epsilon. And this is slightly smaller than m to the 1.5. Then we calculate the time cost for accumulated small changes. We can prove that there are O of m edge updates in the interval point method, and since data structure supports only m beta updates before reinitialization, so the total time for all the reinitializations is m times some polynomial in beta and some polynomial in epsilon. So by equaling these two terms, we get a bound slightly faster than m to the 1.5. This is only a simplified version of the actual trade-off. It has less parameters, but explains the underlying idea. So here is the main components of the algorithm, and we have done with the interval point method and let's begin talking about the locator. Our maintenance of electrical flows is most directly related to the dynamic effective resistance data structures. And the data structure in Goldberg-Rao and Peng in 2019 is obtained by spectral vortex sparsification. In other words, they reduce the problem of maintaining all pair effective resistance to maintaining effective resistances for pairs only in a subset of the vertices, and we call this subset the terminals. The reduction is by random walks onto the terminals, and we will talk about the details later when we use them. Before getting to our locator, let's solve a simpler version first, the checker. For locator, we would like to answer all edges with high energies, and if we can do that, we should be able to estimate the energy of one edge. So the checker supports two operations. The first is to update the resistance of some edge, and second is to curate the energy of some edge. So we hope the update and curate time are both sublinear, and we will use the algorithm from the DGGP19 paper. This dynamic energy estimator is a black box part of the locator, and it also provides adhere to the other parts of the locator, so we use it as a warm-up. Let's first think about this on a static graph. We have physics formulas for resistors in parallel and in series. By these formulas, we can combine many resistors into one, decreasing the number of resistors. And after such an operation, the electrical circuit is equivalent, which means that the energies on the remaining resistors do not change. We would like to do similar things on our graph. We want an equivalent graph on a subset of vertices which preserves the edge energies. So this is called the Schur complement. The picture shows what a Schur complement looks like. We let C be a subset of vertices, and suppose we only care about energies of edges in C. So in the graph to the left, the three vertices in the blue polygon is C, and we would like to calculate the Schur complement of it onto this subset of vertices C. And the resulting Schur complement is on the right. So the Schur complement of G onto C should preserve the energies on edges between vertices in C. Because we have a combinatorial interpretation of the electrical flow by random walks, so the Schur complement can also be explained this way. Remember that the electrical flow is the expected trajectory of a random walk from S to T. So to eliminate some of the vertices and get an equivalent graph on the remaining subset C, the Schur complement should bring any random walk back with the correct distribution on vertices once it goes out from C. So we would like to calculate the distribution of the returning vertex of that random walk. So this formula just says that the Schur complement is the weighted sum of all random walks from C back to C whose interior is disjoint from C. The formula can be turned into a procedure that computes an approximate Schur complement. So for every edge, we sample two random walks from both of its endpoints until they hit the terminal vertex set C, and we connect these two random walks by the original edge into a longer walk, and we add this longer walk into the resulting graph H. And at the end, H will be an epsilon approximation of the Schur complement. That means the edge energies are preserved up to 1 plus minus epsilon. So let's show this by a picture. Suppose we sample random walks from this red edge, then a possible outcome could be the blue random walk above and the blue random walk below. And we connect these two random walks by the red edge into a longer walk, and the contribution of this longer walk is that purple edge in C. By the procedure, we immediately have an algorithm for curing edge energies in C when the graph is static. In the initialization stage, we create the approximate Schur complement by that procedure, and for each curing, we compute the edge energy by an electrical solver, for example, the one by Spielmann and Peng, in linear time, linear in the size of the approximate Schur complement. The advantage of this representation of Schur complement is it can be made dynamic very easily. So we first make it dynamic inside the terminal set C. So what it does to some edge UV completely inside C is that the two random walks ends with length 0 immediately, resulting in a copy of the original edge UV. So all edges completely inside C are trivially copied into H, so we can easily edit them in constant time per update. So if the size of C is sublinear, we get constant update time and sublinear curate time. And for edges not in C, it's also simple to modify them. So we just add them into the terminal set C. If we augment C by vertex V, any random walk sampled in that procedure that visits V before C should now stop at V. So the upper random walk hits V before C, so we truncate it. The contribution becomes an edge between V and the other endpoint of the walk. So since the random walks only get shorter, we can charge the time cost of this to the time for generating these random walks. So the amortized time for augmenting C is a constant. So we can support edge update in constant time. So putting the components together, we get a dynamic energy estimator. In the initialization stage, we sample random walks from each edge. And for augmenting the terminal set C, we just truncate these random walks once they hit the newly added vertex. For edge edits, we first augment both endpoints of the edge into C, then edits are trivial and cost on constant time. For queries, we also first augment C, then the query can be answered by electrical solver on the terminal set C. So this algorithm has sublinear query and update time by setting C to be a sublinear number of random vertices in the graph. We've finished the warm-up. The actual question is not only to estimate energy of one edge, but output out edges with high energies. So the data structure locator should support first update the resistance of some edge, and second, output out edges with energy at least epsilon squared fraction when routing the unit flow from S to T. The general idea of the locator data structure is to reduce the problem to maintaining a dot product. Ken, Nelson-Pert, and Woodruff gave a method that can recover heavy hitters given only a few low-dimensional projections of an original vector. So this theorem applies to our case. We would like to calculate the weighted sum of square roots of edge energies of a random subset of edges. So we can write this sum as this dot product, where the left operand D is the weighted sum of some edge indicator vectors, and the right operand phi is the voltage vector. Our goal is then to maintain this dot product in sublinear time per operation, but the problem is both vectors D and phi has linear length. So we solve this issue by maintaining on a subset of vertices which we call the terminals. So this idea is influenced by the previous dynamic effective resistance paper. So the dot product is turned into a dot product between the voltage vector restricted to the terminal set C and a so-called projection of D onto C, which is a linear function on the original vector D. So then both terms of the dot product can be maintained similarly. For the right operand phi of C, the voltages on a subset of vertices, we can simply call the algorithm from DJGP19 as the Schur complement not only preserves the edge energies, but also the voltages on the vertices. All the components remain the same, except we use an electrical solver to solve for the voltages instead of the edge energies. So this is exactly the same as the warm-up problem. The maintenance of the projection D onto C is similar because the projection can be interpreted as a random walk in the dimension D onto C. So we also sample random walks to estimate this projection value. Let's put the components together. The heavy hitter theorem reduces the problem to maintaining a dot product on a subset of vertices. Then both operands of the dot product is maintained by a data structure. For locating high energy edges, we calculate the dot product by definition. And since the size of the terminal set is sublinear, such a query only takes sublinear time. The last thing is the small issue with how we utilize these randomized data structures. Our analysis requires that the queries and updates to the locator to be independent from the random bits. In our algorithm, the answer of the locator affects the interpoint method, which then affects the queries to the locator. So this breaks the analysis. We solve this issue by partitioning the data structure into two parts. The checker can only check if one edge has high energy, while the locator can return all edges with high energies. As in the picture, when the main algorithm asks for high energy edges, the checker asks for the locator first for candidate edges. Then the locator returns a set of edges, and the checker performs a second check on the edges. This way, the random bits used by the locator is hide from the IPA, and the checker is much easier than the locator, so we only need to handle the adaptivity issue of the checker. That's it for our algorithm. For shock recapture, we reduce the Maxflow problem to augmenting electrical flows. Then we maintain the electrical flows dynamically by data structures. With proper trade-off, these methods combine to a Maxflow algorithm in M to the 1.497 time. Thank you.